Welcome to Gen.Structures 2 and Lateral Forces lesson. What lesson we are? 5 wind examples. This is part 3 of the wind example. And I got cut off last time, and we were trying to figure out the diaphragm shear. And then we're going to select the plywood that we needed, and they were calculate max chord force. And this is on page, what page are we on? 135 of the study guide. So we were going to the UBC table number 23-I-J-1, and that is reproduced on page 98, I believe. And there's a lot of different things you could select. I'm just going to select what they did in the study guide. In their example, it says several diaphragms meet this requirement, and we select the following. And they used 3/8 inch plywood, 3/8 CC with what? Nails. That's 6 inch on center. That's supported panel edges without blocking at the panel edges and without blocking. Alright, and that'll kind of finish up where I got stuck at. And it says this diaphragm has an allowable shear of 160 pounds per foot. So I'll go ahead and write that. 160 PLF, and we'll say it's capacity. So that's greater than the 128. So we're good. Now we will need to calculate the max chord force. I'm going to go ahead and change colors. And for me, the easiest way to look at this, remember we're looking at it where here's your diaphragm. And if you're looking at it like this, here's the building. I believe this building has a parapet, like so. So hopefully my drawing is making sense. So here's the parapet, like right there, and goes around. And then you're looking at the wind force that's coming on this side. We're looking at that. So we're looking at the like that, and then it's going over here like that, and going down like so. All right, hopefully that makes sense. I'm going to scoot back a little bit so it makes it a little bit more clear. That is the wind force we're looking for. It's a pounds per square foot on that plane right there, and it actually got a little bit bigger right there, but I'm not going to worry about that right now. We already have the rest of it. I'm going to get rid of this. So where are we at? Oh, I don't know what we're doing. So we've made that, we've gotten the distribution of that load, and we turn it into a line load coming into that diaphragm right there. And that is the 128.1 PLF. There we go. And if you remember, we took that and we look at it like a deep beam. So here is the beam right here. And you can look at it like if this was an I-beam or a wide flange beam. That looks like this. This is what I mean by look at it like a beam, a really deep beam. It's a 60-foot deep beam. So there's your flange, and the web is the diaphragm itself. So when we're looking for, the whole reason I tried to explain that is the whole reason we want to say that, because now we take this, we rotate it, and we flip it, and we make it look like this, like a simply supported span, where you have 128.1 is your distributed load, uniform distributed load, 128.1 PLF. And if you remember, I don't remember back what it was. You can go back to the other video and see how we got this, but 128.1 times, this is 150 foot, I believe. So 128.1 times 150 foot, divided by 2, because W all squared over 2 is, oh my bad, this is actually 102. I was mistaken. And that's for me not going back, trying to do it by memory. Alright, this is actually what was it? 102 pounds per foot. 102 pounds per foot. Okay. 102 PLF. 102 PLF. And now to get these reactions, it is WL over 2. So that's 102 times 150 divided by 2. We get 7650 pounds. And that's 7650 pounds. And if you want to do your shear moment diagrams, let's change colors. This is the shear at X. You go up 7650, you come down, and it'll hit 0 right there, and it'll go up 7650. So 7650. And then if we look at our moment diagram, this is very simple to do. You will go up at the steeper slope, since this is a higher value. You will level off, the slope will be 0 at the 0 where it crosses the x-axis there on the shear diagram. So we know that slope will be equal to 0 right there, and then it'll slowly decrease more. So you got 0, slope is 0, and it gets heavier. It starts off high and then becomes low, and that's what your moment diagram will typically look like for a uniform distributed load. All right, and we can figure out what this number is right here. This is going to be the area of this triangle. I mean, you can see where integration comes into play, but we don't really have to integrate because we know what the area of a triangle is. 1/2 base times height, so we know it's 7650 is the height, and then this is 150 divided by 2 is 75. So we get, this is 286,875. That's going to be foot-pounds. Does that sound right? That sounds awful hot. And let's think about it. I'm used to foot kips, so that'd be what, 286.8 or 9 foot kips, which is decent, and it's a 150-foot span. Okay, that seems somewhat reasonable. That makes sense. I think that's a correct assumption. Yeah, that seems about right. So at this point, you want to look at this as a beam, and you want to look at the chord force. What is the reason I went ahead and figured out what this diagram is? The chord force is, the best way I like to look at it is to think of it as a truss. So the chord is right here and right here, and your moment arm is between them. So think of it as a coupling, where you could take the moment about the center line, or you could just take the moment about here, and that means you get rid of this chord. So you're going to have this going this way, that going that way. And what is this? This is 60 foot from here to here. So all you have to do is take this and divide it by 2. If you remember the moment, so if we're looking at it's at the halfway point. If we looked at this in a moment diagram and put it on here, the moment diagram would look like, it's hard to show, but it would look like that. So we know the moment, this is 0, this is 0, this is max right here in the center, and that's the 286,875. So we're like, oh, okay. So if you remember, if you've seen the truss videos earlier, you know that you can treat a truss like a simple span. If you're looking at a simple span and you're looking at the truss, then wherever you are on the truss, for instance, if you're looking at the moment, you say, okay, this truss is a simple span, and you look at the middle, it's like, oh, okay, if this were a beam, I would have 286.875 foot kips. But that is distributed, instead of distributed to 2 webs, or not 2 webs, but 2 flanges, top and bottom, you're doing it through chords. So that's the way I like to look at it. I don't know if that might be more confusing the way I tried to explain it there. But anyways, I'm going to move on, and maybe sometimes just doing it helps. So you have these 2 chords right here and right here. Your moment arm is in between, is 60 foot. So you divide this by 60. Divided by 60 foot. you get 4,781.3, and that's going to be what, pounds? Okay, and hopefully that makes sense, because if this is 4,781.3 pounds, and this is 781.3 pounds, you look at the distance between them. If you sum the moment about, let's change colors again. If you sum the moment about this point right here, let's call it A, it's, well, this goes to 0. This doesn't matter because it has no moment on. You sum the moments about A, I said that already. And this one equals 4,783 times 60 foot. Okay, well that's your moment. So that's how you know what it is. And hopefully that makes sense. That's where you're getting this moment right here. Alright, so that is our calculate our chord force. Our chord force is this number right here, the 4,781.3 pounds. Alright, and that was just to finish up. I will go ahead and start on part 4 in a few seconds here, and I will hope this was helpful. If not, go ahead and post some questions and I'll make a video, or I'll just try to answer it in text. Alright, I will see you in a few seconds.